All right, so we're back in business, and we were looking at this problem of these sticker bundles, and what it ultimately came down to is how can we know which of these bundles are similar to one another based on people's actual usage of them, and how and can we can then recommend similar bundles to similar bundles. All right, so that's what we'd like to do. And before the break I asked if we have any suggestions. I think we had one person, Guild, was able to kind of just eyeball it and make a recommendation, but Guild cannot possibly do this if we had 500 bundles and 10,000 users, or he would charge us too much for it. So I would like to come up with a slightly more automated solution to this. Okay. So before, and we're going to use, this notion of vectors with magnitude and with direction. All right. So let's first little recap of vectors. Now I asked you on the homework. I had two required readings, and I hope you got a chance to look at them. One was about some trigonometric concepts like sine and cosine and stuff like that, and the other was about, what was the other one about? What's that? Radians, degrees versus radians. Thank you. I read it, I swear. Okay. All right. So let's talk about vectors, and we'll come back to all these concepts. Okay. So first of all, I would like to look at this problem from the perspective of vectors. All right. So what I'm going to do is I'm going to take these bundles. Excuse me. So looking at this data set, I'm going to recreate this data set bundle by bundle. So the first bundle has three numbers, 1, 4, and 2 for account 1 for these three accounts. Okay, let's put these together. So here's bundle 1. Bundle 1 has these usage numbers for account 1, account 2, and account 3. Bundle 2 has these, bundle 3 has these, bundle 4 has these. Are we happy? Are we okay? I feel like a magician. See, my hands are empty. All right. And then I'm going to column bind these bundles. I'm going to join them by column. All right. And AC bundles now looks like this. Hey, does that look familiar? That should look exactly like this little matrix that I had up here. All right. So I've basically recreated this, and I've created this little set with these bundles and these accounts. Nice, huh? Haven't solved anything, but it feels nice. I feel I've made progress. I should take a coffee break now. Okay. So these are my bundles. And yes, we can treat this like a matrix if you wish. And, if we transpose these, we can see them in this way as well. All right. Um, so one thing I want you to kind of realize is that, so first of all, these are matrices, okay? No longer necessarily simple data frames. This is a matrix. And matrices are made of column vectors and row vectors. In fact, it's the same data. You can either view them as columns or as rows, okay? So in the case of the original AC bundles that I made, here the rows were accounts and the columns were bundles, all right? How do we interpret this? We can think of the rows as the cases we're interested in. And by cases, I mean the people or places or things that we're interested in, okay? And here the bundles are the dimensions in which these accounts exist, all right? So as unusual as it might seem, this data is in 4 dimensions. Dun, dun, dun. All right. This is 4-dimensional data. There's 3 accounts and they exist in 4 dimensions of bundle space. All right. Um, that's a little weird to think about, right? Because typically when we think of dimensions, we think of 1 dimension, 2 dimensions, 3 dimensions, and that's the human experience, right? We don't really think of 4 or 5 or more dimensions. But these exist in 4 dimensions. Interesting. If we transpose the vector, the matrix, AC bundles, then these bundles exist in three-dimensional account space. Huh, that's interesting. All right. So the accounts live in bundle space, the bundles live in account space. Okay. And three dimensions we could just about visualize in three dimensions because, we have three dimensions. Um, Unfortunately for you and I cannot show you stuff in 3D dimensions because I have no three-dimensional tools. So sorry. I will try later this semester to do some 3D demonstrations, but for now, all I have is this projector screen, and the screen is unfortunately a two-dimensional object. It'll be a little hard for me to demonstrate three dimensions on a two-dimensional screen. So let's do this. Let's take a look at one bundle. Yeah, by the way, we can look at the bundles either by columns or by rows. So this is looking at a single row, and this is looking at a single column. Okay, so I hope you remember that from your swirl tutorials back in the day. Matrices, you can look at them column wise or row wise. Okay. The first number, if you the first number tells you which row you're interested in. The second number says which column you're interested in. Okay, so you can look at a single row or a single column. I do want to be able to visualize these a little bit, so let me try it this way. Um, I'm going to plot the transpose of this data, and I'll draw the arrows right away on it, and I'll add some text to it. Okay, what you're seeing here is four bundles. This is going to be difficult. Four bundles in two-dimensional space. I am ignoring account number 3 for now. Please bear with me, okay? I'm ignoring account number 3 for now because it's a little hard to do a three-dimensional plot. It's possible, but then it gets a little weird to compare things. But let's just do it in 2 dimensions because we can visualize 2 dimensions pretty easily. Bang, 2 dimensions, X and Y, right? And these are four bundles, and they exist in account space. So the dimensions are accounts. It's account 1 and account 2, their usage, right? And we're looking at these four bundles not as just points in space, but as vectors. They have direction and a magnitude, but they have direction. Looking at it this way and visualizing it this way, do you begin to see, is it easier now to kind of see, only using 2 accounts, not 3, which bundles might be more similar to one another? Anybody want to tell me 2 bundles that are highly similar to one another? Hello, I can't hear you. 2 and 3? Bundle number 2, bundle number 3. Hey, that's weird. Why did you say 2 and 3? They're so far away from each other. Oh, well, fine. Okay, the direction is the same. Okay, the direction is the same. All right. And what this is telling us is that some people either really love, so account 1 and account 2, they really love bundle 3. They agree on bundle 3. They also agree on bundle 2, right? So these accounts, these different users potentially agree in their taste in bundles, right? Like what what one really likes, the other one really. So for bundle 2 and 3, they're similar in the sense that as much as one likes one, the other person also likes that, and bundle 2 follows a similar pattern. Okay, it follows a similar pattern. It could be now that they haven't used bundle 2 very much, but they agree with each other on their like or dislike of these bundles. Okay. How about bundle 1 and bundle 4? Do these accounts agree or disagree about these bundles? These two, let's call them users potentially. These two users, do they agree or disagree in their fondness or their willingness to use these two bundles. Account 1 really likes to use bundle 4, right? But account 2 couldn't care less about bundle 4. Like literally, they've never used it. It's 0. Account 1 has used bundle 2 a little bit, but account 2 has used bundle 1 a lot. All right? It's a little hard to recommend bundle 1 and bundle 4 because the two users who we have in this even smaller data set disagree on them completely. All right? So what we have here is we're getting a kind of sense of how different people agree or disagree in their usage of bundles, right? Let's play play this a little bit more. If somebody really likes bundle 1, there appears to be no other bundles that people are completely agreed upon in the same direction as bundle 1, right? Which other bundles might you from bundle 2, 3, and 4? Which let's say somebody really likes bundle 1. Which other bundles might you recommend? Looking at this figure, or which one would you really not recommend? Looking at this figure. So if somebody likes bundle 1, what other bundles could you recommend or not really disrecommend, like really not ever recommend to them? What's that? Bundle 4, you would recommend bundle 4 to them? Will not. Okay, because so far the people who really like bundle 1 really don't care about bundle 4, so we probably would not recommend bundle 4. There's only 2 people, but based on this very limited data, maybe if somebody likes bundle 1, we would not advise them to use bundle 4, right? Because as of right now, with only these 2 accounts, the one person who likes B1 doesn't care about bundle 4, all right? And it goes both ways. If somebody really likes bundle 4, looking at this limited data set, we probably would not recommend bundle 1 because the person who really likes bundle 4 so far has no interest in bundle 1 or very low interest in bundle 1, right? So if I had to recommend between bundle 2, 3, and 4 for somebody using bundle 1, which bundle or bundles might I recommend more? 2 and 3? Not a perfect recommendation, but better than recommending bundle 4. If I had to rank order them, then I would recommend, if I had to recommend all of them in some particular order, then I would say if somebody likes bundle 1, I might recommend bundle 2 and bundle 3. And after that, only might I recommend bundle 4 if I had to recommend all of them in some order, right? Okay. So essentially, what we're looking at is we're looking at these vectors and we're making a visual decision. What criteria are we using to make this decision? How are we comparing these vectors when we're making these recommendations? Like when you said, yeah, bundle 2, bundle 3, would recommend one to the other. Or when you said, bundle 1, I would not recommend bundle 4. What metric are you using to compare them? There's a couple of answers here, at least. The distance, right? One is you could use the distance, like from B1 to B4 is very far away, right? From B1 to B2 is closer, so I might recommend B2 to a user of bundle 1. But do note, B3 is almost as far away as B4. What's that? Similar direction. What could you measure to measure whether two things are in a similar direction? Some of you are doing this. The angle. The angle is one thing. Stephanie, did you have another one? The slope. Oh yeah, actually that's interesting. In this case, you could do the slope, but effectively you're comparing angles either ways, right? You're comparing how do they change in angular space, right? That's right. We could actually look at the angles, the difference of the angles between these vectors. So bundle 2 and bundle 3, they have literally no change. There's no difference in angles. There's a zero difference, right? They're the most similar to one another in terms of like the proportional usage. Bundle 1 and bundle 4 seem to be the most dissimilar to one another. Okay. And also, interestingly, if you use angles, then bundle 1's difference from angle 2 is the same as bundle 1's difference from angle 3. It's the same amount. Is the angle is still the same, right? Notice we have not used any statistics yet. We're talking about vectors, directions, angles. Essentially, we're using geometry, right? And that is interesting. We can use statistics to describe many things in day-to-day life, but we can also use geometry. Geometry gives us another model of this world, all right? And here's the interesting thing. Do you remember when you learned geometry in high school or middle school or elementary school? I don't know how advanced you are. What examples did your teacher give you of angles in geometry? Like what examples did you use? Do you remember any of them? There's one example that's used everywhere in the world, I think. What's that? Can you say it louder? Right angle. Okay, but can you give me a real world example of angles that you were taught when you were taught geometry? Rain, map.
For example, like the distance between school and your home.
In angles?
Yeah.
Like if you look at a map, you can draw a vector from school to home.
Yes.
You can draw a vector from home to somewhere else or school to somewhere else, and you can compare angles. Okay, sure. Any other examples? Intersections, like traffic intersections? Sure, sure, but I'm asking for a real world example, not like a geometric term. Intersections in real life? I'm sure you were all asked this question of, here's a building, it's this tall, and the sun is coming in at this angle. How big will its shadow be? Did you not have an example like that? Shadows from buildings? I thought that was like a universal example. Trees, okay, maybe not buildings, but trees, okay? Fine. Or the other way around. Here's a tree. We want to know how tall it is. Here's how long its shadow is. Can you figure out like how tall it is or what the angle of the sun is or something like this, right? It's interesting that a lot of the examples that you were given were like physical examples of like buildings and trees and maps and going from one place to another. The fact is that geometry, though, has got nothing necessarily to do with the physical world. It's just a model of anything you would like to model with it. All right. We're talking about bundles and how similar they are. We're not talking about like how far a bundle is physically from another bundle. You can use geometry to actually describe any kind of phenomenon. It does not have to be a physical phenomenon. It just so happens that when you're young, you're mostly familiar with the physical world, and the examples you're given are physical examples of geometry. But this is a case of where you're using geometric principles to solve a problem that has no physical basis. All right? It's actually purely a fictional or imaginary basis, if you will, right? Um, and it's relating here to human behavior. This is a human behavior basis, not a physical basis. But you can still use geometry. You just did. You were looking at the angles and you were giving me answers. All right. So that's kind of interesting. We can use angles, we can use geometry to answer these kind of questions. We actually don't need statistics yet. Maybe at all. Who knows? Um, Now, if we're going to talk about angles, I do want to, yeah, we have to be careful that angles can be measured in at least a couple of ways, if not more. All right. And I gave you this reading about degrees versus radians. There's two different ways in which we measure angles, all right? And most of us are used to degrees. So with degrees, how does it work? With degrees, where are we? Let's look at this. I'm gonna hide that for a second. So most of us are used to degrees like this, right? 0 degrees, 90 degrees, 180 degrees, 270 degrees, 360 degrees, yes, but 360 degrees is actually 0 degrees, okay? And one of the readings I required of you today is to realize that actually we don't have to measure everything in degrees. Another, actually in scientific computation, a more heavily used system of measuring angles is radians, all right? And radians has this interesting way of thinking of angles. They think of angles kind of like a distance. So radians is like starting from 0, which is like horizontal. Radians is kind of describing how far around this circle you are going, okay? And in this, and you can, and so the distance you're going around, let's call it S. So you've walked from here and you've kind of gone around this far. Or if the radius is this big, then you've gone around this far. Then we describe the angle you have covered as the distance you've walked around this circle, S. That's the distance you've walked, versus the radius of the circle around which you're walking. So S divided by R just gives you the angle in radians, okay? If R is 1, if the radius of a circle is 1, then what is the circumference of the circle if the radius is 1? Does anybody remember this formula for circumference of a circle? It's got pi in there somewhere. You like pi, don't you? Anybody? What's the area of a circle? Anybody remember? What's that? Pi r? Pi r squared? Yeah, good. We got one person. Your geometry teacher's like, yes, I taught Billy well. All right. What's the circumference of a circle? 2 pi r. Oh, okay, you got the r done. Okay. After that 2 pi, you're like, r, I know this one. Yes, the circumference of a circle is 2 pi times the radius r, okay? So 2 pi r. So if the radius of a circle is 1, then the circumference is 2 pi, because r is 1, okay? So if you have so when we're talking about radians, if we use, for example, a circle with radius 1, then the circumference of it is 2 pi, all right? Where half a pi gets you 90 degrees, pi gets you 180 degrees, 1.5 pi gets you 270 degrees, 2 pi is 360 degrees, right? And actually, you can use this to easily convert between degrees and radians. So if I take these quad degrees, quad meaning 4, if I took these 4 degrees and quadrant, like a quadrant, okay, then 0, 90, 180, 270, 360 is actually the same as 0, okay? And these are the quadrants, all right? And if I want to convert these degrees into radians, simply I can do it by using the conversion factor that pi is 180 degrees or that 2 pi is 360 degrees, okay? So I multiply the degrees by pi over 180. Why? Because the degrees are in degrees. 180 is in degrees. It's in the denominator. Degrees and degrees cancel out. Pi is in radians. So I'm given the angle in radians. All right? What is the answer? So 0, 9, actually, let me do this. Let me round this to 2 decimal places so it's easier to read. So 0, 90, 180, 270, 360. In radians, it's 0, 1.57. Aha, I know this number, 3.14. That's pi. That's 180 degrees. 270 degrees is 4.71. 6.28 are actually 0 again. is 360 degrees. Okay, 2 pi. So I just wanted to give you a quick reminder of radians. How many of you studied radians sometime in school? You just forgot what it is. Anybody studied radians ever before? What? No, impossible. Is that a hand? No? Okay, is that one person? I don't even know. Really? I have to pick on people. Edgar, you've never studied radians when you were in middle school or high school?
High school.
In university?
Yeah,
In high school? You never studied radians? Billy? You studied radians. Billy either went to like the best school in the world or he was certainly the best student at that school. I'll say that. I don't know about the school, but okay. Um, all right, fantastic. Wow. Okay, well, not fantastic. I'm being sarcastic. That's kind of crazy. So that's radians. All right. Anyway, now you know radians. Fine, fantastic. That's fantastic. Okay. Do you remember sine and cosine, or do I have to do geometry all over again from scratch? Okay. Um, so I'm gonna skip sine, and I'm gonna go directly to cosine. Okay. So cosine is this function. Okay, how many of you studied sine and cosine in high school or middle school? All of you? Some of you? Many of you? Okay, I'm going to take it as all of you and some people who are checking Facebook. Okay, um, so um, so we have this thing called cosine, and it looks essentially like this. Okay, I can plot all 360 degrees using cosine. This wave should strike you as familiar. Sine is offset by a little bit. It's offset by I don't know how much by pi. I can't remember. So this is what cosine looks like. Okay, and as you can see here, cosine gives you this nice wave. Sine and cosine both give you this very nice wave. We sometimes just call it like a sine wave because that's the S shape of this wave that we have come to learn from when we were younger. And cosine starts with a peak at 0, and at half pi it's gone down to excuse me, a peak of 1 at 0 degrees. By half pi, or whatever the half pi is, it's at 0 degrees. Okay, at 180 degree, it's at -1. All right. At 1.5 pi, or whatever this is 270 degrees, is zero again. And then back to 360 degrees or 2 pi, it's back to 1. All right. Half pi is of course 90 degrees. Okay. Um, so from 1 to 0 to -1 to 0 back to +1, and follows this nice sine wave. Okay. Why are we interested in cosine? Why am I suddenly going back to these kind of principles? Well, whether you're doing degrees or radians, cosine has this really nice property. Well, it's got a couple of nice properties. One nice property is that if you give it angles, it normalizes them between 1 and -1, right? You can give it any angle you want. If you take the cosine, it gives you a normalized value between 1 and -1. Whereas radians is kind of ugly. It's from like 0 to 6.28. And degrees is like 0 to 360 degrees. By the way, why are there 360 degrees in a all the way around? Anybody ever thought about that? Why do we measure degrees in 360? Why not 0 to 100 and make it metric? Why don't we use the metric system for angles? Why do we have 360 degrees? Anybody? You never asked this question when you were a kid? The teacher's like, there's 360 degrees. You're like, I better write this down. 360. Can't be 100. Can't be a nice number. It has to be 360. Anybody? Any thoughts? No particular opinion? You would be happy if they made it 90 or 100 or 200 or 500? Why 360? The Earth moving in 360 days, something like that. But it's not 360 days. It's 365 or 366. You saying it was close enough? They were like, close enough. Let's go get a beer. Like, come on. Mathematicians are pretty rigorous. Never thought about it, huh? Just 360 sounds good to me. Can't divide a circle into 350 or 100 would be nice, right? We like the metric system, things in 100 or 1000. Why 360? Are there any other systems? That's a good question to ask. I just made one up, 100 degrees. How's that? Just separate it into 100 evenly spaced angles. That was easy. I can do another one, 200. I can go all day. So, well, there is another one, radians, 2 pi. All right. Well, as you can see, 360 is fairly arbitrary, right? But there had to be a reason why 360. Why not three? Even if you wanted like a big number, why not 350? Why 360? Let me know on the discussion boards later. Go home, drink some tea, meditate, or Google it. I don't know, and tell me later. Okay, not now. All right. But you can see why mathematicians don't really care about 360 degrees. Somebody just made that number up. So they're going with something that, with a system that they use more in math and geometry, pi, 2 pi, pi. So they're describing it in terms of pi. And in this case, radians is from 0 to 2 pi, which matches very well with the circumference of a circle. As you can see, mathematicians like this a lot more. All right. Okay. So that's just a little thing. And yes, cosine has this really nice property of one nice property that it normalizes angles, whether it's in radians or degrees, it normalizes it to just 1 to -1. We like that. Okay. It's a very nice, because we're going to be using this to describe things. So it'd be nice to have kind of a fixed range to kind of describe things. All right. So let's take a look now at cosine in a little bit more detail. What is cosine and how does it work? So cosine, as you can see, this is the formula for cosine, by the way, if you were ever wondering how to compute a cosine. It's a dot product in the numerator, and in the denominator is the magnitudes multiplied by each other. All right. I swear this is going somewhere. I'm not just going back in time. All right. So let's just talk about how cosine works, because it's going to be really interesting and useful to us in a moment. Okay. So the way cosine works is, do I have it here? Do I have it here? Yes, I do have it here. So let's take two vectors, b1 and b2. Okay. I mean, I'm just going to use the data that we already had. 1, 4, 2, 2, 2, 1. Now you notice these two vectors are in three-dimensional space. They're, because they have three numbers, right? So they're like x, y, z, but I'm calling it account 1, account 2, account 3. They are in three-dimensional space. Okay. Let's break down the cosine formula. The numerator is vector times vector, and actually it's the dot product of vectors. The dot product is defined as two vectors multiplied and then summed. Okay, how do we multiply them? Well, in R, pretty simple. B1 times B2. Do you notice what's happened here? How did R multiply B1 and B2? It basically multiplied it component by component, dimension by dimension. 1 times 2, 4 times 2, 2 times 1. All right? That's part of the dot product. The other part of the dot product is this sum. So the numerator of cosine is the dot product, which is the sum of two vectors multiplied together, dimension by dimension. Okay? So the dot product is 12. What's the denominator? So that's the numerator of cosine. What's the denominator of cosine? The denominator of cosine is the magnitude of the vectors multiplied by each other. Like how long is vector 1 times how long is vector 2? We multiply these two magnitudes by each other. All right? So magnitudes are the formula for a magnitude of a vector. So we write magnitude like this. It's these two pipe symbols on either side. So two lines on either side of the vector. And the formula for magnitude, to compute the length of a vector, is simply the vector, each component of the vector squared, summed, and the whole sum square rooted. Okay, so how does that work? It works like this. Square root of the sum of b1 squared. All right, so essentially what we've done is we've taken each component of this vector, squared it, like b1, it's 1 squared, 4 squared, and 2 squared. We sum those squares. Ooh, that sounds familiar. We sum those squares. Where have we heard that term before? Sum of squares? Variability, actually. Huh. There's something statistical going on here, but we're not talking about statistics. Think about that for a moment, okay? So we are summing those squares, right? We're squaring the numbers of b1. We're summing those squares, and then we're taking the square roots. And that gives us a length of 4.58. Vector b1, which goes from the origin 0, 0, 0 out to 1, 4, 2, has a length of 4.58 in 3 dimensions. So it's a 3-dimensional vector with a length of 4.58. Are you with me? All right. What about b2? Yeah, we can do the same thing. Vector b2. There we are. All right. So it's got a length of 3. All right. Great. So now we have all the building blocks of cosine. We've got the dot product in the numerator, we've got the magnitudes in the denominator, and we multiply the magnitudes by one another. The cosine then, and let me write my own cosine function. You know why? Because R does not come with a cosine function for 2 vectors. Weird. Anyway, it does come with a cosine function, but, well, not for 2 vectors. So I'm going to write my own cosine function here, because R is not kind enough to me. And it looks like this. It looks like this. All right. It's basically my own function called cosine V. I'm calling it cos V for 2 vectors. So you give it 2 vectors, and what does it do? In the numerator is a dot product, sum of A times B. In the denominator is the 2 magnitudes multiplied by each other. Okay, magnitude of vector A and vector B. So let's do this. Let's use this now. Cosine vector B1 and B2. Wow, I get a cosine of 0.28. Interesting. 0.28, 0.87. All right. If I go back, all right, so that's the cosine value. All right. And if I go back, cosine of 0.8 something is around up here somewhere, right? It's around here somewhere. That's if cosine is the y-axis, cosine of 0.82 is up here somewhere. So the angle of between B1 and B2 is somewhere between, I don't know, 20, 30, 40 degrees, something like that. Okay? Looking down here at the degrees. All right? Okay, we're going to get to that in a moment. All right. What else did I want to tell you? Not super important, but oh yeah, I can compute the angle like this. So I've got the cosine. If I want to compute the angle the hard way around, I just do the opposite of a cosine, which is called the arc cosine. The arc cosine gives me the number that's, it gives me the angle basically. All right, the arc cosine gives me an expression from 1 to -1. The arc cosine gives me an angle, but this angle is in radians because R, like most mathematical software, prefers to use radians. I can compute this to degrees. It's about 30 degrees. So the angle between B1 and B2 is about 30 degrees. Okay. Cosine captures this really nicely with a value of 0.82. So cosine is also giving me angles. Cosine is yet another way of measuring angles. It just normalizes the angles between 1 and -1. So Edgar, you asked me, is there any other way of measuring angles? Now we have 2 more. We have degrees, we have radians, and cosine is another way of measuring angles. Whereas degrees is from 0 to 360, radians is from 0 to 2 pi, cosine gives us a really nice upper and lower bound, 1, -1. Much easier, okay? Much less arbitrary, at least. So essentially, cosine is just another way of measuring the angle between two vectors, of expressing the angle between two vectors. It's a normalized expression of the angle. Normalized because it's between 1 and -1. All right? Whew. Quick summary of what cosine is. Why do we care? This is the money slide. All right? So what we can do now is we can actually compute, if we want to know which bundles are similar to which bundles, we can just measure the angles between them, right? One way of measuring it is, yeah, we can take it and we can do all these kind of funny angular measurements. The other way is just express the angles as cosines, no problem, right? It's pretty simple. I'm going to use a library called LSA. Anybody know? You have to install it first. You have to install packages LSA. It comes with a really handy dandy cosine function, which can take an entire matrix and compute the cosine between all the different columns of the matrix. Okay, so when I run this cosine function that comes from this LSA package, all right, this tells me the angle between every single vector of bundles, between every pair of vector of bundles. Bundle 1 versus bundle 2 versus bundle 3, bundle 4, all the possible combinations. All right? You notice that if two bundles are exactly the same and they agree with each other, like bundle 1 and bundle 1, its cosine is 1 because its angle is 0. Right? So if two things agree perfectly, the direction is the same, there's no difference in their angles, the cosine is 1. If two bundles disagree with each other a lot, do you remember two bundles that really disagree with each other? 1 and 4. If two angles disagree with one another, 1 and 4, we get something closer to 0. Okay? Why? Because in this picture, at least, the furthest two bundles can be from one another is 90 degrees. And 90 degrees is half pi or pi? It's half pi. It's half pi? It's half pi. And 90 degrees is half pi. The cosine of that is 0. All right? And bundle 1 and bundle 4 come the closest of any of them to 90 degrees. It's got about, and its cosine value is about 0.22. Okay? Now, to make all of you happy, because you're paying my salary here, I've also expressed them. I've just taken this cosine matrix, taken the arc cosine and multiplied it by the conversion factor to get degrees. So this is actually the degrees of difference between each of these bundles. Bundle 1 and bundle 1, 0 degrees. Bundle 2 and bundle 3, also 0 degrees, right? Bundle 2 and 0, 3. Bundle 1 and bundle 4 have the biggest difference, 77 degrees. All right. Interesting. We're solving this problem of recommendation systems in this way using geometry, not using statistics. But I give you a hint that there might be statistics involved, because remember, in the magnitude computation, we had the sum of squares that suddenly pop up. Think about that. There might be something statistical going on, but this is purely geometric, right? From here, so I just showed you this matrix of angles and degrees just for your understanding. You can ignore it. Let's take this cosine bundle. We can now recommend bundles based on their cosine similarity, their similarity based on cosine, right? Of course, I don't want to recommend bundle 1 to bundle 1. That would be ridiculous because you're already using bundle 1. But I could look at the next biggest number, like 0. Yes, I could recommend bundle 2 or bundle 3 if you like bundle 1, right? For people who like bundle 1, I would recommend bundle 2 or bundle 3. I would probably recommend bundle 4, the last option, okay? Now, I've shown you the code this far. there's two more steps, and I'm not going to show you the code for that. I'd like you to play with that as your homework assignments. Essentially, I want to have a matrix like this, where for each bundle, I can have my first recommendation, my second recommendation, and my third recommendation. I don't have a fourth recommendation because there's only 3 other bundles in this bundle of 4, okay? So for example, for bundle 1, I would recommend bundle 2, bundle 3. My third recommendation, my distant recommendation would be bundle 4, okay? And similarly for bundle 4, I would recommend 2 and 3. Bundle 1 would be the distant recommendation, all right? For bundle 2 and bundle 3, I would recommend one to the other because they have the exact same vector direction of their vectors, right? And they have cosine. Bundle 2 and bundle 3 have a cosine value of 1. Their angle agrees exactly, right? How can I arrive at this recommendation matrix? There's a couple of jumps that I took, okay? One jump was that from this matrix of cosines, I produced another matrix that looks like this. What this is showing you here is I'm basically telling you which bundles, I'm sorting these cosines and writing down the name of the corresponding bundle in a matrix, okay? This might also take 2 steps to get here. So then for B1, I've got B1, B2 to B3, B2, B, like this. The first column is useless because, it's recommending bundle 1 to bundle 1. So I can get rid of it. And then I have this recommendation matrix. Okay. I will leave this as a homework assignment to you, but I will offer you a plenty of help if you ask on the discussion board how to do this. All right. But essentially, I've shown you most of the steps to go from, this kind of a data set all the way to this cosine matrix. And then I'll leave it as an exercise to you to figure out how to produce this recommendation matrix. All right? It'll be a little challenging, but help each other online, please. Help each other on the discussion boards. Feel free to say, I have no idea how to begin, and ask people, what's the first thing give me a hint. What's the first thing I should do? Okay? And let's help each other figure this out. What I have effectively shown you is a big part of a recommendation system known as item-item collaborative filtering. All right? If you've heard of this, that's great. If you haven't, now you have. All right? And it uses cosine similarity to create recommendations based on, and it's called a collaborative filtering technique. We're basically taking information from all the users of the system, in this case, only 3 accounts, but we're using everyone's information to come up with a collaborative answer, to collaborate, to come up with a single for answer to this question of which bundle should I recommend to each other. Okay. Anybody know who first proposed this as a technique for recommendation systems? Anybody want to guess? This idea of using cosine similarity to do recommendations was, as far as I know, was first published by Amazon not so long ago, maybe just like in the 1990s. And they said, hey, this is an interesting way in which to do recommendations. And I'll actually share that paper with you as one of your readings for this week, okay? Again, not required, but if you're a student of data, you should read it, It was not that long ago. You were all around frolicking and doing stuff. I don't know what you were doing, but and Amazon came up with this idea of, hey, we can use cosine similarity to find for them similar products that they can recommend. Okay, here are similar bundles. It's the same idea though. Cool. By the way, this LSA package, what is this? Is this a geometry package? What kind of a package would have a cosine function, do you think? Anybody know what this LSA package is for? It must be some like crazy geometry package, right? Why else would we use cosine? Let's go take a look. LSA package R. Click. Oh, that downloaded the PDF. I don't want the PDF. This is a package for latent semantic analysis. Huh. Any idea what that's for? It's essentially a package that's used to find semantic meaning in data, and it's probably used more for like natural language processing or something like this, okay, to process human language. So it's being used in a proper data analytics framework, right? They need to compute cosines. And here we are also in a data analytics environment, and we're using cosine. So cosine is used heavily for as a similarity metric between vectors. All right. So this has been all very interesting, and I'll ask you to do this on a much larger scale, on a very big data set as your homework assignment, to kind of go through these steps and produce recommendations. All right. It'll be an interesting exercise, and you could then say you've produced a rudimentary recommendation system. All right, so that's kind of cool right away. Of the kind that you get when you go to Netflix or Amazon, like that's how they're making recommendations to you. This is one of the ways in which they make recommendations to you. There are others. All right, so that's kind of cool. All right, um, now I'm very puzzled. When I asked you earlier, oh, where is it? When I asked you here, how do I find which bundles are similar to one another? I threw you off by telling you we're going to use vectors. If I just gave you this as a data frame and I asked you, how similar is column 1 with column 4? What's another way of telling me how similar two columns of data are? Anybody? What's that? You have to speak louder. T-test? That tells you the means. I'm not interested in the means. I have two columns of data. I want to see how similar they are. Anybody? Who said that? Thank you. Ding! Correlation. You've known correlation this whole time. Nobody suggested, hey, just check the correlations between these columns, right? You let me go on this big rigmarole of like vectors and cosine and this and that. Yeah, we could just take the correlation of these things, and that would be another metric that tells you how similar or dissimilar things are. You remember correlation? Yes? Excellence. Cool. So if we and correlation actually has some nice properties too. It's also a normalized metric from 1 to -1, just like cosine, right? Remember in our cosine matrix, the cosine similarity matrix that we produced, when two vectors are very similar, go in the same direction, they agree with one another, a high cosine similarity, meaning high similarity, is 1, right? And technically, in our data set, the lowest cosine can be 0, can be a 90-degree difference. However, cosines, if you allow for negative values, can get as low as -1. That would be two vectors going in completely the opposite direction of each other. 180-degree difference would give you a cosine of -1, right? Means two vectors that completely disagree with each other. So let's re-examine cosine. If they completely agree, same direction, cosine of 1. If they are orthogonal to each other, meaning if they are 90 degrees with each other, that is not disagreement. That just means they're independent of each other, right? Do you agree with that? That's why we often draw graphs with x-axis and y-axis as 90 degrees to show them as independent of each other, all right? So if they're independent of each other, then we have a cosine of 0. And if they're two vectors going in the opposite directions, we have cosine of -1. What about correlation? When two things agree with each other, they have a correlation of 1. When they are completely disagree with each other, they have a correlation of what? 0? -1. So correlation goes from 1 to -1. Complete disagreement is yeah. If they are independent of each other, the correlation is 0. If they completely disagree with each other, like, you know, um, every time I drink tea, you drink coffee. Every time I drink coffee, you drink tea. That would be -1 correlation. All right. So that's a complete disagreement with each other. When I drink tea, I cannot predict what you will drink. That's 0. Your decision is independent of mine. Okay. That's interesting. Correlation and cosine have exactly the same properties. 1 to -1. 1 is high agreement. -1 is total disagreement. 0 is independent decisions. Right? Could we use correlation instead of cosine? Could we use correlation for similarity? Here's the formula for correlation. Does it look familiar or similar to you? Big picture, not exactly the same. Are there any aspects of the correlation formula that look similar to something we have seen recently? The numerator is two things multiplied together and summed. The denominator is something squared and then summed and then square rooted, multiplied by the other thing, squared, summed, and square rooted. Where have we seen this formula just like this? What's that? Cosine. This is exactly the same, almost the same formula as cosine. Recap, cosine's formula is right here. It's vector A times vector B summed. That's the dot product. The denominators are the two magnitudes, which is vector A squared summed and squared. Vector B, the same thing. Let's look at the formula for correlation. The formula for correlation, if we treat these as vectors, is what is this? What the hell is this, by the way? What's going on there? What's that? It's A minus, it's some values A minus, what is this? The mean of A. What do you call this expression when you take the mean of something away from it? Mean center. Mean centering. It's mean centered. It's vector A mean centered times vector B mean centered divided by the magnitude of vector A mean centered times the magnitude of vector B mean centered. In fact, correlation is just a mean centered version of cosine. That's all it is. All right. So if you've ever wondered why does correlation find similarity between things, it's doing geometrically exactly what cosine does, is looking at the angle between two vectors. All right. If the angle is 0, you get a high correlation. If the angle is 180 degrees, you get a -1 correlation. If the two angles are 90 degrees, you get a 0 correlation. You've been fooled all these years. What is known as correlation is simply a cosine, but it's a cosine of mean-centered vectors, okay? And that does produce different results. Those same three vectors, A, B, C, if I mean-center them, then this is what the picture looks like. If I mean center them, then the origin is now at the center of my picture, okay? Earlier, the origin was at the bottom left. I've mean centered it. Boom, the origin has moved to the center of the picture. B1, B2, B3, B4 now look like this, okay? Some things overall are the same. Like B1 really disagrees with B4. It's more apparent in correlation than in cosine. Once you've mean-centered it, the difference is more apparent. B2 and B3 are still good friends. They're going in the same direction. Aha, but notice something. Now they have the same magnitude. They have the same direction and the same magnitude now. All right? So one way of computing correlation is to mean center everything and then do a cosine. That'll give you a correlation matrix. Let's try it. So I'm going to do this a little, this may look a little weird, but let's try this. So I've done cosine similarity, I think. Let's do correlation. Bang. So to do correlation, here's how I'm going to do it. Well, there's two easy ways. There's an easy way and a hard way. Here's the easy way. You just call the car function. It gives you a correlation matrix. All right, this is my correlation matrix. Some things should look similar to the cosine matrix. The diagonals are ones, and B2 and B3 have, a correlation of 1. They also had a cosine of 1. B1 and B4, they had a very small cosine. Now they have actually a fairly large negative correlation. Okay. And how do we do it one by one? So first of all, what does mean centering mean? When we mean center a bundle, right? When we mean center a bundle, so let's mean center all the bundles. Let's take all my bundles and compute their means. Bundle means, this is the mean of all my bundles, of the 4 bundles, okay? 2.3, 1.6, 3.3, 1.0, okay? I've just used an apply function, and I've taken the mean of all the columns of these bundles. The apply function allows you to say whether you want columns or rows, okay? All right, so that's the mean of my bundles, all right? I am now going to produce a matrix which is just columns B1, B2, B3, B4, but now the values are just their means, nothing else. The values are just their means, repeated. So I use the replicate function as you saw here. All right, I replicated the mean vector multiple times. Okay. Now to mean center all my data, all I have to do is take my original data and subtract from it the bundle means matrix. Okay, I'm subtracting the means from all the numbers, and this gives me a matrix. Oh, let me round this off because this is very ugly. This gives me a matrix of mean-centered column vectors. Each column has had its mean subtracted from it. Okay, so this is B1, column B1, but now you notice some numbers are negative, some are positive, because each has the mean subtracted from it. Each value has the mean of that column subtracted from it. It would be impossible, I think, for any of these vectors to have purely positive or purely negative numbers. They must be now centered around 0. Each of these bundles now has a mean of 0 because I've mean centered them. Okay? And now to compute the correlation matrix, all I have to do is just take the cosine of this mean-centered matrix. And this gives me, if I let me round it to 2, this gives me the same value as the correlation matrix. All right? Excuse me, let me round these numbers to 2. So this is the cosine of the mean-centered matrix, and here is the correlation matrix, AC bundles. Ah, will I ever get it right is the question. Let's do this again, and we'll say it to 2 spaces. All right? Ta-da! Correlation is nothing but a mean-centered cosine. Okay? So if you've ever wondered in the back of your head, how does correlation work? How does it give me a similarity metric? One way to think about it is geometrically. If you were to mean center all your data, it's just telling you the angle between the mean-centered data. That's all correlation is doing. Okay? Now you notice that the results are fairly similar, almost the same. I can't remember. Are they exactly the same or almost the same? B3, B3, B2, B2. B3, B3. It looks like it's just about the same, but they won't be always exactly the same. In this case, it's exactly the same, but it won't be always the cosine similarity matrix and the correlation similarity matrix will not be exactly the same. They'll be similar though, okay? And actually, recommendation systems sometimes use cosine. In fact, they almost always use cosine, but they sometimes use correlation or some other kind of adjustment. There's one other kind of adjustment from cosine matrix. It's called an adjusted cosine matrix. Instead of mean centering the columns, you can also mean center the rows and then take the cosine. That's just called an adjusted cosine, all right? Technically, there is row-centered adjusted cosine, and correlation is just column-centered adjusted cosine. Okay? So that's correlation. All right? So essentially, today I wanted to introduce you to the concept of correlation, but I've come about it a very different way. I've come about it by trying to explain to you geometrically what correlation does. And it's kind of crazy that correlation, the formula for correlation, was not derived geometrically. This is a breakdown of what correlation actually is. Okay? Let's take two sets of numbers, x and y. You can think of them as vectors, but now we can go back to a statistical notion of just two columns of data. Okay? You know how to compute their variability, right? The variability is you mean center one of the values, you square it, and then you sum it. That's the variability, right? You can do the same thing for y, right? The variance is when you take the variability in the numerator and you just divide by the degrees of freedom, right? That's variance. There is a notion called covariance. Covariance is interesting. It's almost exactly the same formula as variance, but in the numerator, rather than just taking one variable mean-centered and squaring it, you multiply it by the mean-centered version of the other variable. So it's mean-centered x times mean-centered y instead of mean-centered x squared, okay? So it's mean-centered x times mean-centered y summed divided by the degrees of freedom. It's almost exactly the same as the formula for variance, except we've just changed one of these with the other variable. Okay? That gives you what we call a covariance. How do these things vary together? Now, if you take your covariance as the numerator and you divide it by the product of the two standard deviation of x and standard deviation of y, you get correlation. This is the statistical explanation of what correlation is. Correlation is the covariance of two variables. What does their dispersion look like together? Their covariance. Fully standardized. Remember, when you divide a number by it, when you divide a variable by its standard deviation, we call that standardized. Actually, when you mean center a variable and divide by the standard deviation, we say that number has now been standardized. This is a fully standardized covariance. We're basically taking the covariance of x and y and dividing it by the standard deviation of x times the standard deviation of y. We're standardizing the covariance by both the x variable and the y variable. That's a correlation. Okay, so a statistical explanation of correlation is it's a fully standardized covariance of two variables. All right. A geometric explanation of correlation is it's a column mean centered cosine. They're exactly the same thing. The two formula are exactly the same. Okay. If you were to derive the formula from angles and geometry, then correlation would look like this. If you were to derive it from statistical principles, it would look like this. They work out to be exactly the same thing. All right? So geometry and statistics are really just two different ways of describing the world. And when they agree perfectly because they are just two models of the world. One is a statistical model, I guess, a numerical model of the world. One is a geometric model of the world. But they're telling the same story just in two different ways. Okay? So in this thing we call data analytics, we are doing statistics and we're doing geometry. We're doing the same thing, whichever perspective you want to take. This is a kind of dualism. The two things are there's two perspectives on the same problem. All right. So anyway, one of the spin-offs of this long exercise of coming to correlation but the geometric way was you have also in the process developed a recommendation system algorithm. That's a nice spin-off to have. Okay. It just so happens that people doing recommendation systems find that the basic cosine works better than the column-centered cosine or correlation, just generally speaking. All right. The other version of cosine, the row adjusted, when you mean center the rows, which is again like correlation, but you just mean center the rows instead of the columns, that also produces oftentimes slightly better recommendations than a correlation does by itself. But they're the three same thing, just how you want to mean center the values. Okay. For your homework assignment, I'm going to give you a very large data set and ask you to do the same exercise. I'm going to ask you to come up with cosine-based recommendations, with correlation-based recommendations, and with adjusted cosine recommendations. Okay? And we'll come back the next week and we'll discuss what's the difference between the very minor adjustments, mean centering adjustments of the cosine. All right? Great. But overall, I do hope you get a sense now that data analysis is not just a pure statistical thing. We can think of it as a geometric thing as well. All right. And geometry is this beautiful thing that we can use to describe the physical world, but we can apply the same tools to describe any other kind of world, including a four-dimensional bundled space worlds. Or, as your homework is going to be, I think it's going to be like a 300 or 400 dimensional version of this problem. All right. The number of dimensions is not an issue. It's got geometry has nothing to do with the three dimensions of this world. It can handle as many dimensions as you want. Okay. It's just another perspective of these problems. Okay. So, okay. So that's, I have one last thing to do, but let's just take a little stretch break. Woof. That's a lot. But I hope that gives you some enjoyment, not only in solving a problem of how do we compare two sets of data together, but why we sometimes describe them as vectors and geometrically, why we sometimes describe them statistically. Um, and also, you've been able to solve a real-world problem. There's many other interesting things you can do with the tool you've just developed. For example, let's make this something closer to your world, maybe. Let's say account one, account two, and account three are just, person one, person two, person three. And bundle one, bundle two, bundle three, bundle four are hobbies like taking a walk by the seaside, watching movies, eating food, hanging out with friends. We can use the same thing that we've done. Instead of recommending bundles to one another, we can do things like recommend hobbies to one another. Or we could transpose this matrix so that the people are the columns, and now you have a matchmaking service. You have a dating service that matches people based on their interests, right? That's how a dating system works. So this is a pretty powerful tool. You can go out and make a dating service. You can make a movie recommendation system. You can make whatever the hell you want. All right. Um, you could also do the following. Instead of account one, account two, account three, you could, excuse me, instead of bundle one, bundle two, bundle three, bundle four, you could also make this like book one, book two, book three, and book four. These are books you're reading. And these, instead of accounts, we'll have words. Like we'll take a word, like take 1,000 words, and in the matrix in the middle will be how many times each of these books uses these words. Now you have a way of finding books that have similar topics. Ta-da! All right, it's an incredibly powerful system to find similarity in data for multiple things. All right, I can see all the brains like, oh, I'm gonna drop out of school right now. Make a bookmaking service. Yes, perfect. Sorry, Jeff Bezos already did it. It's called Amazon. All right. Okay. Are you done stretching? Little stretching? Are you okay with this? All right. So we've talked about data similarity today. What makes data similar to other data? And the simple system that we used was cosine similarity, which you can think of as a kind of correlation, right? No, no, the other way around. Correlation is a kind of cosine similarity. That's the conclusion of this today. Okay. All right. Anything else? Oh, one more thing before I let you go. But I'm gonna cover it very lightly. The next topic we're going to cover in the coming weeks is going to be regression, linear regression. Okay, and I think you've all seen regression before, so not a big deal. But I would like to rethink what regression is, like the way we rethink what everything is in this class. We rethought what uh, hypothesis testing is. We rethought what correlation is. We're going to rethink a little bit about what regression is. Okay, but in rethinking it, I'd like you to play with a little exercise, and I'm going to give you a very simple story here. I think I've just got like 2, 3 slides, so don't worry. I'm going to go through this quickly. I'm not going to cover what regression is today. That's the next 3 weeks, okay? However, I want you to be able to see that, correlation gives us, first of all, a sense of what is similar and not similar in data. So let's take this really stupid example that I just wrote down by myself. This data is completely fictional. I just wrote it down, okay? So let's say we have restaurant store. What was this example again? Um, I'm going to completely remake this example again. Forget that first column. Okay, let's pretend we have some different cities in Taiwan, like maybe Hsinchu, maybe Taipei, Kaohsiung, Taichung. All right, and we want to know how many students live in this city. All right, so the student population of a city. And some small cities maybe have 2,000 students. Oh my God, some big cities have maybe, let's say, 26,000 students. Okay, the next column is how much pizza they're buying. How much pizza is sold in this city? Okay, so 50. So let's imagine there's a restaurant and it's got branches in every single city in Taiwan, and in some cities they sell like let's say 58,000 NTD worth of pizza. In some cities they're selling, my God, 202,000 NTD worth of pizza. That's a lot of pizza. Um, we can plot the student population versus the sales of pizza. And we see a figure like this, okay? I can read this data and I can perform a variance analysis. I can ask, what's the variance of this data? It would tell me the variance of students. So that's the variance of this column. The variance of students is 63 point something. The variance of sales is 1,700 something, okay? That's cool. That's a variance function in R. Hey, do you notice one more thing? In this variance, it gives me a variance matrix. The diagonals are variances of students and the variance of sales. What's this off diagonal number, 315? Meta, louder.
Covariance?
It's the covariance. This is actually called a variance covariance matrix, okay? The diagonals are the variances, the off diagonals are covariances. It makes sense because covariance and variance have the same freaking formula. If you just replace one of these terms with another variable, you've got covariance. So if you apply the same formula on all these columns, when the two columns are the same, you'll get variance. When the two columns are different, you'll get covariance. Okay? So that's a variance covariance matrix. The off diagonals are covariances. We can also get a correlation matrix. And remember, correlation is a fully standardized covariance. It's just the covariance divided by the standard deviation of one variable times the standard deviation of the other variable. You're fully standardizing it to both variables. So that gives you a correlation. And now the correlation here is, so the correlation of each variable to itself is meaningless. It's 1. Okay, it perfectly agrees with itself. The off diagonals are the interesting correlations. So the correlation of sales and students is 0.95. This is one way of expressing the relationship between these two variables, students population and sale of pizzas. That's making me hungry. Anyway, we got a few more minutes. There is another way. So we're going to now start talking. In the previous semesters, we were comparing like the difference between two variables. Now we're going to be talking about the relationship between two variables. All right. Cosine is one way of describing the relationship. It's the angle between the vectors that those two variables represent. Correlation is another. It's also a cosine of mean-centered, all right, vectors. All right. There is one other way. At least there's many other ways, but there's yet another way of describing the relationship between, let's say, two or more values, and that's regression. All right. Let me just show you quickly how a regression works. No. How to run a regression. We'll talk about how it works later. How to run a regression. In R, you just take your dependent variable, the variable you're trying to explain, and you use this tilde sign to create a model to separate it from the independent variable, the variable you're using to explain the sales, the number of students in this case. And you just call LM, it stands for linear model, and that gives you a regression object. If you take a summary of that regression object, it will tell you certain facts about it, like the relationship between students and sales is 5.0. Does anybody know what that number means? Anybody remember? Stephanie, you're on it. It's okay. Close, but not that's not quite it yet. But you're tantalizingly close. It's not how well your model explains it. It's actually an explanation of sales based on students. Does that help? Regression effectively tries to draw a line through your data, right? So this is students versus sales, scatter plots. Regression tries to draw a kind of trend line through your data, okay? And says, here's a line that kind of explains the relationship between these two variables. What do you think the 5.0 here means? It's the what? Beta. This is one of the betas. Somebody said it here. It's the slope of the line. It's literally the slope of the line. Okay? So, and Stephanie, actually the slope of the line does tell you a lot about how well the model fits, but there's something else for that as well. Okay? This is the slope of the line, and 5 tells me for every student I add to a city, for every student I add to the city, the sales goes up by $5. Uh, excuse me. I should look at the units a little bit more. For every 1,000 students I add, the sales goes up by 5,000 NTD. Okay, unit by unit. Okay, so it's a slope expressed in the units of the two variables. Okay. How many of you have seen a regression before? Please help me out. You've seen a regression before? Yes, most of you, all of you. And those and other people are checking Facebook, right? So that's the slope of the line. Question: does that line run? How would you describe that line versus the scatter plot of data? Where does that line run? What is that line doing? The distance? How would you describe this line relative to the data? Is it running through the data or outside the data? Through the data. Through the middle of the data or on one side of the data? Through the middle of the data? Is that line running perfectly through the middle of the data? We'll answer this question in the coming weeks, okay? I have one little exercise I want to do for you to do for homework, and it's fun and easy for me. um, it looks like the following. Where is it? I'm going to give you a function called interactive regression. Ah, interactive regression. And I want you to run it. And when you run, this will be the second question of your homework. When you run this um, function, you will get an empty plot on the screen. This is the fun part now. You use your mouse cursor and you can start plotting points on the screen. And it will give you some information. It will tell you the slope of the regression. That's the slope of this line. And the intercept, that's like where does this point, raw intercept. No, ignore this and the scale for now. It'll also tell you the correlation. All right. So the intercept, okay, intercept is where does this line cross zero on the y-axis? No, when does it cross? Where on the y-axis does it cross zero on the x-axis? So zero on the x-axis is here. So it's crossing zero at about 4.47 on the y-axis. That's the intercept, okay? It gives you the intercept, it gives you the slope, and it gives you the correlation of x versus y. And I'm going to ask you some questions about regression, correlation, about regression and correlation, okay? So I think it'll be a fun little exercise, and you can just visually plot this thing out. If you're, I know what you're wondering. You're saying, screw regression. I want to know how you do this fancy simulation. So the function is right here. I've provided some comments of what the function does. If you can make sense of it, that's great. If you can't, you're welcome to ask me. You don't have to know how it works. I just want you to have fun playing with it and doing a few simulation exercises with it, okay? All right, great. So that ends our discussion of correlation. We're going to move on to regression next week in class. Thank you and have a great week.